Example B. Okay, so here's another example where you're asked to find the interval of convergence for a power series. Since it was important in that last example, I'll start out this example by noting that this power series is centered at 3. And I get that from this x minus 3 expression here. So I know that this power series converges at least when x equals 3. And the interval of convergence may extend further out from 3. But whatever I come up with for an interval of convergence, it should be centered around 3. If it ends up lopsided on either side of 3, then I know something's gone wrong. Okay, and again, I know it's centered at 3 because the general form for a power series is something like this when it's centered at A. And so in this case, the A is 3. Okay, so now, where does it converge? I would start this with the ratio test, like I did with that last example. I use ratio tests most often to start out these interval of convergence problems. If you're considering the root test, you're going to end up taking the nth root of n plus 2, which could, be a little bit of a pain to deal with. So that's why I would just stick with ratio test in this example. So I take the limit as n approaches infinity of the absolute value of the n plus 1 term. And I've said in a previous video, so powers of -1 are just either 1 or -1. When you take the absolute value, they're always just 1. So if it's going inside an absolute value, we can drop out that -1 to the end, because I know it's just going to be a 1, times x minus 3, so in place of n, put n plus 1, over, in place of the n here, put n plus 1 plus 2. So all of that over, so I'm dropping the -1 to the n because it's in the absolute value, x minus 3 to the n over n plus 2. There's the nth term. This is an plus 1 over an. Okay, so now we need to simplify. So this is equal to the limit as n approaches infinity. So this expression right here I will write as x minus 3 to the n times x minus 3 to the first. I'm going to run out of room, aren't I? Hold on. I'm going to start over down below. Go ahead and work, ahead of me. So x minus 3 to the n times x minus 3 to the first over n plus 3. And then I'm going to multiply by the reciprocal of what's down here. So n plus 2 over x minus 3 to the n. Okay, so x minus 3 to the n cancels, and that's it, right? But now this expression, x minus 3 to the first, is no longer dependent on n. So again, it doesn't care about n approaching infinity. It's unaffected by that limit. So I can pull that out in front. So this is equal to, it needs to stay inside the absolute value though. Absolute value of x minus 3 times the limit as n approaches infinity of, so what's left? Just n plus 2 over n plus 3. Which that right there, so ratio of two polynomials with the same degree. So limit is the ratio of the leading coefficients, which is 1 over 1. So the limit here, using ratio test, turns out it's equal to the absolute value of x minus 3. Okay, let me erase this stuff. Erase the work that I did below. So remember, ratio test says that this series converges when the limit, which in this case is equal to absolute value of x minus 3, is strictly less than 1, right? Okay, so solving that inequality. If you have absolute value less than a number, then the way to solve that, let me write a rule for you off to the side here. So the rule to apply in these absolute value problems, if the absolute value of u is less than a number n, then that expression u is between positive and negative n. Whenever n is a positive number. So if you have the absolute value less than some positive number, then you should take what's in the absolute value and put it between positive and negative, whatever that number is. So maybe that's hard to read, but what I mean is, so in this case, the u is x minus 3. So if absolute value of x minus 3 is less than 1, then that means that x minus 3 must be between -1 and +1. And then if you add 3 across all three parts of this inequality, you have 2 is less than x is less than 4. So interval of convergence goes from 2 to 4, which is good to see because that's an interval that's centered around 3. Where the radius of convergence, so if it converges here, the radius of convergence, how far it extends out, is 1 in this case. Radius of convergence is just how far out from the center does the series converge. Now something else. The ratio test also says that this series diverges when the absolute value of x minus 3 is greater than 1, which is going to be when you're out here, either less than 2 or greater than 4. Then the absolute value of x minus 3 will be greater than 1. So it diverges out there. Also, ratio test is inconclusive when x equals 2 and when x equals 4. So if this is our limit, if we plug in 4 for x, then this limit is equal to 1, and ratio test is inconclusive. Same thing if we plug in 2 for x here. You have absolute value of -1, which is 1. Ratio test is inconclusive. And so this is the way it's going to play out every time in these types of series, where you have a finite interval of integration. You're going to probably be using ratio test or root test. So you'll say it definitely converges inside this interval, it definitely diverges outside, but it's inconclusive at the endpoints. So you end up having to check the endpoints individually. So let me do that now. So checking the endpoints. Let's start with x equals 2. Okay, so if x equals 2, first thing you do when you're checking endpoints is substitute that x into this power series expression. So this will become the sum from 0 to infinity of -1 to the n times, if we're letting x equals 2, then this is 2 minus 3 to the n over n plus 2. Okay. And so that's -1 to the n times this is also -1 to the n over n plus 2. And so that's -1 to the n plus n, so 2n over n plus 2. And so for any integer n, you're going to have -1 to an even power. I mean, that's what an even power is. It's a multiple of 2. So if this is always to an even power, then that numerator is just 1. So here, taking a step back for a minute, when you're checking endpoints, you substitute the x, and then most of your effort is going to be spent just simplifying the series for that particular x value. So we've simplified this to the series 1 over n plus 2, and now you just decide, okay, so how do I want to check convergence or divergence of that series? You could do the integral test. You could also do limit comparison test. That's probably what I'm going to choose here. So with that series, I would do limit comparison test with the series 1 over n, the good old harmonic series, which we know diverges. If you take the limit as n approaches infinity of our given series here over 1 over n, you'll have the limit as n approaches infinity. Bring this up, flip it over. It's going to be n over n plus 2 when you multiply that out. So ratio of the leading coefficients is 1 over 1. The limit's 1. With limit comparison test, if your limit is a positive finite number here, then the series behave the same way. So since we're comparing it to a divergent p-series here, or the harmonic series, which we know diverges, then this series must also diverge. So when x equals 2, we've determined that the series diverges. So the interval of convergence, what we know so far is it's going to go up to 2 but not include 2. On the other side, it's going to go up to 4. Now we just need to know, is it a bracket or a parentheses at 4? Should we include 4 or not include 4? So we need to check that endpoint. So I'm going to erase this, and this is the one last bit. These problems are very long when you're finding interval of convergence and you end up having to test endpoints. But let's see. So now, if we check x equals 4, so if I substitute 4 for x in this expression for the series, then this right here will be 1 to the n, which will always just be 1, right? This is going to be some power of 1. So this right here, 1 to the n, will just be 1. And so we end up with the series negative 1 to the n over n plus 2. When you plug in x equals 4 here and simplify, this just becomes 1, so you end up with just that series. Okay, which you take a step back, you decide, okay, how would I like to test a series that looks like this? And I would say your best bet is alternating series test. So you check those two conditions. Is the limit as n approaches infinity of these terms the non-alternating piece, so we get to just call this 1 over n plus 2. That's 0, which is what we need to see, so we move on to the second condition. Is a n plus 1 less than a n? Is it are these decreasing terms? So 1 over n plus 1 plus 2 would be less than 1 over n plus 2. Yes. So it satisfies both of those conditions, so it converges by the alternating series test. This series converges, which is when x equals 4. Dropped the marker. Okay. Converges when x equals 4, so we do include 4. So all of that to get this answer here. The interval of convergence is parentheses 2, comma 4 with a bracket. It does not include 2, it does include 4.